This is the first lesson of Module 4 on vectors. Here we are introducing the idea of vectors and scalars. These are two different types of physical quantities that we're going to see in this class. A vector is a physical quantity that has a magnitude and a direction. The magnitude is the number and amount with a unit, and this quantity is always positive. The magnitude is always positive. The vector also has a direction. Direction is usually defined as an angle or angles measuring the orientation of this quantity. Although we've seen in one dimension, the direction of the vector can be described with a plus or a minus sign to show which direction along the x-axis. So there are many different vector quantities that we're going to see in mechanics. Most of the quantities we'll be dealing with are vector quantities. And so, for example, we have velocity is one example of a vector quantity. The magnitude of the velocity is the speed. That's how fast you're going. We would measure that in meters per second, miles per hour, and so forth. And then beyond having a speed, you also have to have a direction. You would be traveling at 15 meters per second north, or 25 miles per hour at an angle of 150 degrees, for example. In contrast with vectors, we have scalars. Scalars are another physical quantity, but they are completely described by simply a number and a unit. So they're just an amount. Mass, temperature, energy, entropy, time, these are all scalar quantities. And so you don't have to define the direction when you're describing the mass of an object. The mass is just something inherent to the object. That said, even though this is a scalar is just a number, scalars can be negative. So your temperature, for example, can be positive or negative, whether you are above or below some reference temperature that you were measuring against. But that doesn't have a direction associated with it, right? It's just a measure of the thermal energy of the object. When we are describing a vector, there's a couple of different ways that we can do it. We oftentimes want to represent a vector graphically when we're drawing a picture and trying to understand what's going on. A vector has to have a magnitude and a direction, and so we can describe the vector as an arrow. The length of the arrow represents the magnitude. So if I have a vector A, I use the overhead arrow here to denote that this is a vector quantity. The length of that arrow is the magnitude. A without the overhead arrow means that that is the magnitude of the vector A quantity. The direction the arrow is pointing in represents the direction of the vector quantity. So that's the direction of motion if it's a velocity vector. That's a direction of the push or pull if it were a force vector, and so forth. When we want to quantify or put a number to the direction of a vector, we're going to use an angle phi to describe the direction or the orientation of a vector in 2 dimensions. Angle phi is measured counterclockwise, starting from the positive x-axis, and measured counterclockwise to the direction of the vector. This is what we're calling standard form of that angle. The pointy end of the vector is the tip, and the other end of the vector is the tail. If you are measuring a vector, you put the tail of the vector at the location where you are taking that measurement. The magnitude is a number with units. It's always positive. We typically write it as A without the overhead arrow, or this is the sort of mathematical formal representation. This is like the absolute value because that's the amount of the vector. I usually use this format when I really want to emphasize the fact that this is the magnitude of a vector quantity. If you want to write the vector numerically as a number or as a pair of numbers, you'd write vector A here would be its magnitude at an angle of phi, where phi again is measured in standard form. This is the more mathematically formal representation. I don't like this little symbol because it tends to look like a greater than sign or less than sign when I use it, so I use a little at symbol. But either way, to distinguish that you have a magnitude and a direction is sufficient. When you are including an actual number for your angle, make sure you are including the degree sign. And vectors are defined by a magnitude and a direction. You can't change the magnitude and direction. That's part of your measurement, but vectors are not defined by the location. You can pick a vector up and move it, and it's still the same vector. So as long as vectors point along the same line, they have the same direction because they're pointing along the same line, and they have the same length, that makes them equal vectors. So here you see two different vectors A that are equal to one another. There are different ways to combine vectors, and we're going to see that through the other lessons in this module. One place to start, though, is the multiplication of a vector by a scalar. When you have a vector quantity, you can multiply by a scalar, multiply by a number. Recall that scalars are just a number with no directional information. And so when you multiply the scalar towards the vector, it's going to change the magnitude of that vector, but it can't change the direction because the scalar has no directional information. So it's going to stretch or compress the vector, but it's going to point in the same direction, or it's going to point along parallel lines. The new units of this product of a vector and a scalar will be the product of the units of the original vector and of the scalar. We'll see many more units as we move into future modules. If you want to divide by a scalar, before we move on, let's say here is vector 2a. Notice that vector 2a is along a parallel line as vector a, but vector 2a has twice the magnitude of vector a. When we multiply by 2, we're doubling the magnitude, but we're pointing along parallel lines. If we were to divide by a scalar, that's the same as multiplying by the reciprocal. So if you divide by 2, it would be the same as multiplying by a half. So if I take vector a and I divide a by 2, it gives me the same vector pointing along parallel lines, but with half the magnitude. Or if I multiply vector a by a half, again, same direction, half the magnitude. Multiplying by a negative scalar reverses the direction. Here, if I have vector a and I multiply by a -1, negative a has exactly the same length. They point along parallel lines, but in opposite directions relative to one another. These are called anti-parallel. When you have two vectors that point along parallel lines, but in opposite directions along parallel lines, we call them anti-parallel vectors. And finally, if you multiply a vector by 0, you get what's called a null vector. A null vector here has 0 magnitude and undefined direction. 0 magnitude, if the vector doesn't exist, then there's no way to define what direction it's pointing in.